The group of optics and computer science of the Popular University of Caesar within the framework of the Seminar of Optics is allowed to present this video.
The objective of this video is to train students in the methods of studying, analyzing, designing, and evaluating the technology's applications of optical sensors implemented with optical fibers.
The Campinas University in Brazil and the Popular of Caesar University in Colombia developed the microresonator polymer fiber capillary for measuring the pressure in microfluidic. We demonstrate how fiber optic sensors could be used in industry, and how custom optical fibers makes a difference. The general situation is that fiber optic sensors are used in demanding environments and in a variety of enterprises.
First, we consider the evolution of optical sensors, the importance of fiber optic sensors, their main technologies, and key devices, components, and subsystems that allow the implementation of fiber sensor systems. The video description is: Experimental manufacturing and assembly. Experimental results. Theoretical results. Conclusions.
In this research, a device for the measurement of hydrostatic pressure. The field inside this cavity is coupled through a taper fiber. The theoretical and experimental results show a sensitivity dependent on the geometric parameters of the manufactured optical fiber.
The fiber drawing tower is a multi-story machine with precision alignment that is used to draw the preform into an optical fiber. The preform is a multi-layered cylinder typically 20 cm in diameter and 2 m long too. The tower has several subsystems needed to achieve the correct balance of temperature, which affects glass viscosity, and draw tension. Key subsystems include the preform feed module, the heat source, the capstan at the bottom, and the coating apparatus.
Manufacture of capillarity fiber. Microcapillaries are manufactured from a commercial PMMA preform tube. To stretch the optical fiber, it is required to heat the preform tube. Microcapillaries were obtained with wall thickness in the range 30 to 400 micrometers and external diameters 100 to 300 micrometers.
Capillarity fiber manufactured in the laboratory with external diameter 689.04 micrometers and wall thickness of 46.13 micrometers. Thin-walled capillarity fiber image. Image thin-walled capillarity 34.85 micrometers and large outer diameter 934.37 micrometers.
Fiber taper. A commercial SMF 28 Corning fiber was used. The flame sweep heating technique was used. The fiber is stretched while being heated by the flame. The manufacturing technique allows the thinning of the fiber with adiabatic profile. The system is controlled through LabVIEW to ensure a slim fiber with the appropriate parameters.
We report the fabrication of adiabatic tapered optical fibers using a low-cost heat and pull rig. Our setup is based on the flame brushing technique moving in zigzag, where an inexpensive and simple portable gas microtorch is used as heating device. Since this method does not require an electronic system to control the gas flow rate, makes out taper rig an attractive alternative, low cost, and trivial to implement.
In the figure can be observed the general diagram of the experimental setup, including uncapillary resonator, manometer, and nitrogen cylinder. The microscope image showed the taper fiber coupling.
Experimental results. The displacement of the resonance peaks of the analyzed samples was experimentally verified and the Q factor was determined. In physics and engineering, the quality factor or Q factor is a dimensionless parameter that describes how underdamped an oscillator or resonator is. It is defined as the ratio of the initial energy stored in the resonator to the energy lost in 1 radian of the cycle of oscillation. The figure showed the displacement of resonance peaks as a function of pressure.
Experimental results. The experimental sensitivity of each of the manufactured samples was determined as the variation of the displacement of the resonance peaks on the pressure applied to the interior of the optical fiber. Physically, the sensitivity of the resonant device defines the ease of spectrally shifting the central wavelength of the resonance peak. The reproducibility of the experiment and its stability were verified. The figure showed the graph of reproducibility and the sensitivity of sample. Reproducibility refers to the ability to repeat an experiment and obtain the same results, while sensitivity refers to the ability of a test to correctly identify positive cases. And the graph of the spectral stability of the resonance peaks. The reduced spectral width in the zero dispersion regime offers new opportunities for frequency stabilization in applications of frequency standards.
Experimental results. The table showed the sensitivity and geometric parameters of the analyzed samples.
Theoretical results. The modes Whispering Gallery WGMs can be detected. Whispering Gallery modes, WGMs, are surface modes that propagate azimuthally around resonators with rotational symmetry, toroidal, spherical, or, as in our case, cylindrical shaped, since the optical fiber itself plays the role of the microresonator. The light is reflected around the edge of the resonator, creating a standing wave that amplifies the light and produces a laser beam.
Theoretical results. To perform the theoretical analysis, the cylindrical symmetry of the capillary is taken into account and the polarization of the modes is analyzed independently, that is, the TE and TM modes. For the case of polarization of TE modes, the refractive index and the solution.
The theoretical sensitivity was obtained by solving the eigenvalue equation for the resonance wavelengths for the first modes. Similarly, solutions were found for TM modes, finding that they are generally smaller than TE modes.
The numerical simulation, a method of finite differences in the time domain. COMSOL multiphysics. The figures showed the simulation in COMSOL with a taper fiber diameter 4 micrometers, capillary wall thickness 4 micrometers, internal diameter 30 micrometers and cross-sectional view of the coupled system.
Conclusions. Capillarity fibers can be used as microfluidic hydrostatic pressure sensors. The experimental results obtained in the experiment agree with the theoretical results. TE modes are more sensitive than TM modes. Sensitivity is optimal the wall thickness of the capillary and its external diameter. Sensitivity improves when the thickness of the capillary is smaller.
For more information, see the publication.